And you can see that basically, if you have the concept correctly, you can finish the quiz in about 10 minutes. Okay, that is the purpose to sort of keep yourself sort of synchronized with the class, so that you don't fall behind. At least you see into this class, and then you can more or less catch the next material. Okay, so the quiz is just help you to sort of synchronize your learning progress together with the schedule of this class. And usually it takes about 10, no more than 15 minutes for you to complete it. And you can open your notes, you open computer, open everything, try to understand it, and then obtain the quiz sheet. Okay. All right. So for today, you can continue your quiz during the break, so you don't have to worry about that. Okay. So I want to finish the second part of the chapter 0. Basically, this is a review on electromagnetic wave, and this is in fact a big part in your textbook. Okay, and I think the textbook assumes students who haven't taken the electromagnetic wave and try to give a lot of details, but we need to move on really quick. All right, this is not in your textbook, but from my point of view, very important to your learning about dispersion of material. And if you are from the electrical engineering background, you should be very much familiar with this. This is a linear system. Okay. Li Xiaolong, you want to study electrical engineering, right?
Yes.
Have you taken the course on signal and system?
Yes.
Yes, right. That is very important class. And when we talk about linear system, we talk about superposition. And the beauty or the trouble with this work is that the time flow in one direction. And have you thought about how to reverse the time? That is going to be very hard, but you can find in science fictions, right? But anyway, up to this point, we follow the rule that the time will go forward only. So this means that the causality also applies. And if you want to see something, you need to cause it first, and then it will happen. If you don't prepare for the class, then you will have difficulty with the quiz, right? All right, so linear system is a simple and straightforward system to model, and then that facilitates our understanding about the ensemble effect of electromagnetic wave. So think about that you have a linear system, and then you kick it, just hit it like this, and then there's a response. The response is that you hear something, right? I hit it, and then you hear something. That is a response of this. And to model the whole thing, I could just do a simple experiment. I hit it, and then you hear something. And then later, if I hit it twice, you hear the superposition of the two responses in time. And then if you just add them together, you construct the whole solution. So if I later give you an excitation like this, then you superimpose the 5 responses according to the time of the excitation, then you get the full response. So this is the beauty of the linear system. Okay. So suppose that you partition your excitation into data function, and then later when you put some continuous wave into the excitation, you could construct the output based on this superposition principle. So this is what we call this linear system. When you do superposition over time, you'll be doing integration over time. So this is the basic idea of the linear system. Any question about this? Okay. So you have the response, and then now the excitation is weighted. The excitation is a weighted data function. Okay, there's a data function that has infinite narrow in time, but there's an infinite magnitude, but the finite energy is limited. So when you do an integration of this over time, you get some finite energy, and then we normalize the energy to 1. Okay. Now this one can be modeled by the superposition of the delta function over time. That is the basic idea. Therefore, you do this integration. The response is weighted by the magnitude of your excitation. And then you do a time integration to add everything together to get the response. So this is the basic concept from your linear system class. Is there any question about this? So everybody understands this the convolution kind of the calculation, right? Linear system. If you haven't taken the linear system or signal and system class in electrical engineering, but you have taken Fourier analysis, some classes on engineering mathematics or in physics, then you will also know about this, because this is a basic concept from Fourier analysis. Agree? Is it difficult to you? Ioannis is the name. Ioannis.
Giannis.
Ioannis.
Yeah. No, these are all familiar because I have taken all these courses, but I took them maybe 2 years ago.
Okay.
So everything's familiar. I have seen them before. I have passed the courses, but it has been over 1.5 years since I last studied them.
I see.
So I need to brush up my knowledge.
Okay, it sounds reasonable. I took this course about 30 years ago, but I'm learning every year. But it is quite natural that, well, I try to illustrate one experiment, right? If I hit it, then you hear something. And then if I hit it twice, then you hear the superposition of the two responses, okay? Even though you don't have to wait the second excitation, the first excitation, in fact, ring over time. The response, in fact, ring over time. So if I hit it twice, you need to integrate over all the time, but not just just one instance. Okay, that is why this integration. Okay, because this result ring over time, but this excitation is like just hit it in one instance. That is why this integration. And that is because that the response follow the causality, the sequence of your excitation. So it has to build a causal system. But to do this integration, you need to make sure that this is a linear system. Okay. When I hit it, then it does not couple the result of the second excitation. Okay. All right. So now, if this is the also shift invariant, this means that if I delay the excitation by this amount of time, the response is also delayed with the same amount of time, then this is called shift invariant. Now, I can just shift the response. H is a response. We call this the impulse response, right? So I can just shift the response by the same amount of time and then add them together. So this is simple and beautiful, except that you need to deal with a convolution integration. Okay, and you saw this in Fourier analysis as well. All right, is there any question? Well, in electrical engineering, quite often that we deal with the response in the frequency domain. Okay, and so we need to understand the time domain response. At the same time, we can also analyze the response in the frequency domain. Okay, so this is a sort of straightforward. Okay, now this plot, the excitation is not going to be so so beautiful that it's just equal amplitude. Well, for an arbitrary excitation, there could be amplitude variation over time. So later, we're going to have decompose the excitation into some data function, but it's a weighted data function. Okay, weighted by this form. Well, ideally, you can get a concept with this kind of data function excitation, and then you have the same response. But if the excitation is some sort of curve, okay, so apparently this magnitude is different from this magnitude. So this is going to be the data function weighted by some sort of excitation function. Okay, so when you do this integration, there's a weighting function here. That is the your excitation. Okay, so suppose well, this kind of excitation can be arbitrary. But in electrical engineering, we like to deal with time harmonic signal, right? Time harmonic signal is like this in complex notation, cosine, sine, and that will be interesting knowing that if I have a time harmonic excitation, what is going to be the output? So this is the most interesting tool in electrical engineering, because we deal with time harmonic function. And therefore, whatever arbitrary function, that can be synthesized from time harmonic function by virtue of Fourier analysis. Okay, so if you know the response of time harmonic function, you pretty much know everything about this linear system. Okay, for any arbitrary function that can be synthesized from the time harmonic function. So let's put an input, a unit amplitude time harmonic function into this system and see what happens. Turn out that the output look like this. The output look like this. If you put this into this convolution calculation, very simple calculation, just put it inside, and then you end up having this results. Okay. Well, this result gives you some prefactor that is a function of this frequency, and then also the unit harmonic function. So you put a unit harmonic function into this system. The output also has the same oscillation. This is what the linear system tells you. Okay, any question? This is the first result that I want to tell you. If you put this into the system, the output is going to be also this. Simple, right? Conceptually simple. But that is modulated by this function. Turns out that this function is the Fourier transform of the impulse response. So the output, if I have an input like this, the output could be like this. Okay, the amplitude is different. So it tells you that when the frequency is different, you have a weighting factor coming from this term. And this term is the Fourier transform of the impulse response. So this term tells you how this system responds to a sinusoidal signal. And we call this system transfer function. Okay, this name associated with this. We call this system transfer function. So in the frequency domain, well, you have the unit excitation, harmonic excitation to this linear system, and then the output is also a time harmonic function modulated by this system transfer function. By knowing this, you pretty much know everything about this linear system. Okay. This is a very important experiment. In fact, if you want to know the characteristic of a linear system, then put a sinusoidal function, put a sinusoidal signal into the system, just hook it up by using a coaxial cable, and then send it into the system, and then measure the output. And if you go over some frequency range, then you can construct this. Okay, you can construct this. And then you understand this linear system completely. Because when we work in electrical engineering, we want to know how different frequency excitation, how this is going to respond. Okay, and if you do an inverse Fourier transform, then you go back to the impulse response of the system. So ht, this the small letter ht, and this capital letter hf form a Fourier transform pair right here. If you know ht, if you know this hf, then you know everything about this linear system. All right, and this offers one experiment for you to quickly construct this. Don't forget that think about you are doing one experiment, okay? And then you put a sinusoidal signal into this. And then the output is a sinusoidal signal, but weighted by this system transfer function. So this is a good experiment to do, because after you do this experiment, you have this system transfer function, and you know everything about this system. All right, is that the question? All right, what if I don't put a unit harmonic function here? If I put some sort of magnitude associated with it, well, the output is simple. If I put 2 here, then you get 2 here. Okay, so this is the linear system. You put 3 here, then you get 3 here. But don't forget that the characteristic of the system is associated with this term, h of f. And how is this related to optics? Well, let's treat this guy, glass as a linear system, and try to send lasers, for example, with different colors through this. And then let's try to understand how this guy responds. Because in our model, this is a linear system. Okay, and this is how we understand the dispersion of a material. Remember that in the last lecture, we have optics, right? We have the UP, UG. That is a function of frequency. That is a function of frequency. Okay, so we have DUP over D frequency. If this is not 0, then we say that the material is dispersive. And what exactly in this is a function of frequency? Well, UP is equal to almost over K. That is equal to C0 divided by refractive index. The term associated with the frequency is this guy, refractive index. And this comes from dipole response of the material. Okay, so we want to figure out how this guy is relevant to the frequency of the excitation. Then let's treat this as a linear system and do the calculation. Okay, so let's go to the simplest configuration that hey, we have some dipole inside, and then that is a linear system, and then we try to do superposition and figure out all the dispersion. All right. So now in the linear system, so we just have some conclusion that well, if you have a unit harmonic excitation, then the output is going to be also a harmonic signal weighted by the system transfer function. And this system transfer function is the Fourier transform of the impulse response in the time domain. Okay, so this is sort of the conclusion from the linear system. And then now let's think about material. Well, if I go into this class and then I send a laser through it, the electric field of the laser is going to pull charges, right? So let's just imagine that you have dipole charges inside this, and then they are holding together by the Coulomb force. Therefore, they look like a screen. Those are not free charges. It cannot move freely like in the metal, but they are sort of attracted to each other, and then they oscillate. And let's treat this as a linear system and try to understand how this is going to look like. All right, so you see the rationale, the reasons that we went through this. Okay, is there any question? Good, right? Right, so let's look into the origin of this guy. The origin of this guy comes from this the sensibility of the polarization density vector. And we define the polarization density vector, well, in the time domain, that is the time average, it's the volume average of all the dipoles. So this is the dipole moment, right? So P basically is a lot of dipole moment, P, small p. And then when we talk about volume average, then we need to calculate number of those dipoles per unit volume. So this N is the number of the dipoles per unit volume. And then we create this polarization density vector in the time domain. Okay. Now we need to understand this. Well, you calculated this before, right? You know Hooke's law, so you construct this equation. When we deal with the spring, I'm sure that you see this before. If you have some oscillation, that is the F equal to minus K X. K is let's put the H here. K is the Hooke's constant for spring. Everybody see this before, right? Everybody see this before, and this is equal to MA. A is acceleration, and so this is M, X, the double derivative of the displacement. It's the second derivative of the displacement, right? Everybody knows about this. And then, what is different between now? The excitation here, in fact, comes from the electric field. Let's just put this into Q. Okay, the force now is the electric field in the laser. So this is all understood, right? And if you move this to the right-hand side, so if you move this to, for example, to the left-hand side, then you have M dx square dt square plus force constant x equal to your excitation. So this. Okay, and if you take this to M, take this to downstairs, this is the resonant frequencies shown here. Okay, so we are constructing this. What is missing from this equation? Is this term. Okay, this term tells you that hey, in this system, there's a resistive force to sort of react to this force. That is proportional to the velocity. This first derivative is the velocity. So when the spring going like this, when the spring going like this, there's a certain force resisting this motion. That is proportional to the velocity. So think about this, that this is sitting on this, and when there's an excitation doing this, there's a temperature rise here because of friction. And this resistive force is proportional to the speed of this guy moving on this. Okay, that's why you have this. So this is called damping constant. Gamma is called damping constant. Okay, that receives the motion of this guy. So you have everything in this equation. You have excitation from the electric field of the laser, and then you have this acceleration term, and you have this resonance term, and then there's damping in this process, represented by this gamma coefficient. We call this damping constant, and this is the excitation from the electric field. So you know how to derive it. Okay, for one single dipole. If I have the response of the one single dipole, then I can construct the polarization density vector according to this formula. And don't forget that previously we know that this refracting index n squared is equal to epsilon r is equal to 1 plus chi this chi e. That is the electronic susceptibility, right? Yiqian, remember this, right? We don't know yet what this is. In this expression, we don't have this. We don't have this. In this expression, we don't have this yet. Now we want to understand what this is. If I know what this is, then I know what refracting index is. So this is the whole purpose. Okay. Any question about this? I hope this is clear. Now we want to find out this. We don't know what this is yet. If I know this, then I know the refracting index. So I need to know this in front of as a function of frequency. So I know this as a function of frequency. Then I know the dispersion of the material. Okay. So look like this is not going to be a time domain parameter. It's a frequency domain parameter. And we're going to show you that in fact, this is the transfer function of this dipole. Okay, when we talk about transfer function, it's a frequency domain parameter. All right, so we have an equation to work with. Let's put this excitation into this and see what happens. Okay, this is a linear system. You have excitation that is a harmonic signal weighted by some amplitude. So let me go back to remind you. Right, if I have a harmonic excitation, unit harmonic excitation, I get a result which is also a harmonic signal weighted by the system transfer function. But I told you that if I put 2 here, you also put 2 here. If you put 3 here, you also put 3 here. It doesn't matter. You can extract this system transfer function. Okay. So now, what did you put? You put a factor here. It's just a constant coefficient. Don't worry about that. So you put it into this, and then you write the output. Well, this is the displacement you want to find out. You write the output into also harmonic signal, because this is a linear system. All right, so solve it. Put this into this and put this into this. You can solve for this. And this is the output, right? And you want to compare this with, in fact, now you know that this x0, in fact, is going to be the system transfer function multiplied with this. Previously, I told you that this can be 1, 2, 3, 4, 5, whatever. Just put it into this. This is your output. All right. So the solution is like this, right here. So it's modulated by the amplitude you put in. So this is the system transfer function of this guy. It's a function of frequency. So for different frequencies, you see how this guy will respond. Okay. and there's a damping factor. It's a complex function. So there's a real part, imaginary part, and also phase associated with this response for one dipole. Well, now you can construct this to get a polarization density vector because this xt is given by this, and then you're writing this part as this. Okay, so we're one step closer to the final results. But now we are talking about the frequency domain quantities. All right, so we'll have this. Let's continue. But don't forget that this is the system transfer function of the dipole. Okay. All right, so the excitation like this. Important thing is that this is a harmonic excitation. So the output is also a sinusoidal signal weighted by the system transfer function and also amplitude. Okay. And the dipole response. Now the dipole response right here, this is polarization density vector in the time domain. If we know this, we can write it. And if this is sinusoidal function, this is also sinusoidal function. So very straightforward. We write like this. There's a certain phasor in front of this sinusoidal function. Okay. So let's put them together. This is the definition. So this is volume density of all the dipoles. So we're talking about a chunk of material, not just a single dipole. We're talking about a chunk of material, average over the volume. The response is given by this macroscopic concept, polarization density function. All right, so we have all the solutions. We have this for this, right? And we have this from the last page. Just copy down everything, put them together. You end up having this P, the phasor of the polarization density vector function given by this. All right. So this is the sort of the system response. The system response of a chunk of direction material. If you excite it at different frequencies, you have this. Right. Now, the electronic susceptibility, in fact, is defined in the frequency domain. It's in the frequency domain, okay? Because we want to know how this is going to be changed over time. We want to figure out how this refracting density is a function of time. So this, the electronic susceptibility is defined in the frequency domain. Okay. So previously we knew that we wrote P equal to epsilon naught, high E. Previously we have this from electromagnetics, right? In fact, this is a phasor. Don't forget, when you write this linear relationship, those two are the phasor. We're talking about harmonic functions, sinusoidal functions. Therefore, we have this. So this means that this is specified at certain frequency because E and T are sort of real parts of E phasor, T phasor, exponential J omega T. Okay. So this linear relationship is defined in the frequency domain, not in the time domain. Okay. So let's divide this with epsilon E by taking out this to the left hand side. You have this electronic susceptibility function. Okay, so I put it here. Be careful that you don't write this P as this. There's nothing like this. Okay, this only holds in the frequency domain. Okay, so once you have this, and then you have the electronic susceptibility function, then you have this a little bit ugly expression. That's the real part imaginary part associated with it. Now we want to understand the role of the real part and the imaginary part. And don't forget that the omega, well, in this class, I adopt the notation of frequency, like 2 pi. I try to make it consistent with for this lecture, okay? So I define, sometimes that especially in your textbook, frequency is written like a new, okay, and in my lecture note, I try to adopt this F as a frequency. So you need to sort of switch a little bit. All right, so now we end up having the electronic sensitivity look like this, a real part, imaginary part. And after 10 minutes, we'll continue this to understand the physics. And you have time to finish your quiz.